Hello and welcome to session 205 in the AISafety.com reading group. Tonight we'll be discussing the article An Empirical Model of Large Batch Training by Sam McCandlish, Jared Kaplan, and Dario Amodei. So these are three researchers from OpenAI, and they're also thanking the contributions from the OpenAI Dota team. This was published in December 2018, which was just a couple of months before GPT-2. So quite a few things happened after this. There's an accompanying blog post, and it's at least somewhat related to AI safety in that they thank Paul Cristiano for his contribution. Paul Cristiano is mostly working on the AI safety part of OpenAI. So what does this paper actually have to do with AI safety? I think this is a quite reasonable question to ask, because this seems to me like, well, on the face of it, it has nothing to do with AI safety. This seems like a very, very standard machine learning paper. And I think there is some value in, just every once in a while seeing a bit of that. This seems like, good quality research, and if you think GPT-3 will lead to AGI, then I suppose this could be on the critical path to AGI. And these kind of small conceptual advances that this paper represents, whether those are hard to come by or easy to come by, is one of the big questions that are debated among the people who discuss whether an intelligence explosion is likely or unlikely to happen. So in my personal model of AI research, there are three tasks that need to be done. There is some conceptual work, there is some mathematical formalization of this conceptual work, and then there is some engineering and some testing to figure out whether this actually works. So to put it bluntly, I think that the engineering and testing is some work that is well understood, in the way that if we are trying at some point to build towards an AGI, then there will be some work to be done with testing it and engineering it and scaling and all these kind of things. But this is something that I feel is understood. In the same way, writing things down in a very mathematical, formalized way, it's very hard, and I couldn't do it, but it seems quite plausible that if you have some ideas, then formalizing these ideas, these concepts, you just go to the Institute for Mathematics and take a number of graduates there, and basically they can do all the mathematics that are required. What I think is interesting are the conceptual and philosophical ideas and breakthroughs. To me, this is what we are missing in order to get AGI. We don't really need more people who know mathematics or more people who can set up testing and this kind of thing. The key thing is, how hard is it to truly, in a philosophical sense, understand what is intelligence and how can we build it? And then there's also the practical point of view, in that for me here, presenting is a lot easier for me to present the conceptual ideas rather than the formalism and the engineering part of this paper. So we have a paper here, and I'm only going to focus on 1/3 of it, the conceptual philosophical. I will say a few things about the others, but not very much. Okay, let's start about to explain what the paper is about. I'll give a very, very simplified overall description of, well, basically AI. So we have some input, maybe a picture of a cat, and this is a sample from a larger space. In this case, it might be the space of all images. It could be basically anything, and we stochastically take a sample of that, and then we run it through a neural network, and then from this we get an output saying this is a cat or this is not a cat. In supervised learning, we get some kind of error, and the thing we're really interested in here is what is called the gradient, and the gradient is how the weights of the neural network should be updated in order to classify this image more like a cat. And this is very often visualized with a 2D height map, where we are trying to get to the lowest possible level, and then the gradients are like the arrows that say, in order to get to a better trained network, we need to go in this direction. So once we have this gradient, then we can basically change the weights of the neural network in order to go down the descent of this. And since we take a stochastic sample, this is what is called stochastic gradient descent, which is one of the most basic AI algorithms. Okay, great. So that's the basic idea, and obviously we want to this is a mathematical object, a mathematical algorithm here, and we want to actually implement this. And we are not going to wait 18 years or however long it takes to train a human. We would like to have this done very soon. Unfortunately, the Danish 16th century astronomer seems to have observed that actually moving this light or electricity or things here, we can't do that arbitrarily fast. There seems to be some kind of limit. So just scaling this up basically doesn't work. So, but we still have our deadline. How can we do that? Well, one thing we can do is we can take this and basically copy paste that in 10,000 or a million different pieces. So we basically for each of these we take a stochastic sample. So if we copy this into a million pieces, then we take a million samples, which is what we call a batch. We run this through the network, and then we get a number of gradients, and we average all the gradients. So it becomes somewhat less stochastic. You could say in the limit we take the set of all possible images, and then stops being stochastic gradient descent. Then it's just stochastic. Then it's just gradient descent. But in the more realistic sense, we have like a not maximal batch size. But we get some gradients that are now averaged out, and those we put in and update the neural network and copy paste it again, and then we run this loop again. So the big question here is, how large should these batches be? Because we can see if we copy paste this a million times, then it takes a million times as much compute. But hopefully we can get done a bit faster. So to visualize this trade-off, you can see here we have on the y-axis compute cost and the x-axis training time. And then we have a deadline. We need to be done in 1 week, and we have a budget. It can't cost more than $1 million. And that gives us an area of the economical feasible region for what we can do. And then there's a problem, which is technically feasible area here, where since there's an overlap, it means the project is feasible. We can actually do that within our budget and within our deadline. But you can see that we actually have choices in here. We can choose to have it done as quickly as possible, but use up all our budget, or we can use a bit less hardware and then use all our deadline, or somewhere in between. Those are basically our options. So how does this look in practice? Well, it depends a lot. Whether the problem is feasible, of course, depends on how hard the problem is. You could imagine here we have the a very, very simple problem, training a tariff breakout to only get a score of 10. You can either choose to use a bit of compute or a bit longer training time, but it's basically this. If we want to have a score of 500, then we'll need to, spend either more compute or more training time, or most likely quite a bit more of both. So one of the things that makes this go faster according to our deadline is what is called the learning rate, which is how large steps do we take along the gradient. So here you can see a very simple 2D map where you can see we want to basically go here, and then if we have a large batch, which means that we have a good gradient, then we can take a good step towards this along this gradient and still be basically okay. But if we have a small batch, then we'll have a gradient somewhere in between this big red area here. And if we take a long step along this, well, we might end up with a worse solution than we had before. So here you can see this visualized. We are starting here and want to end up at the minimum here. And if you have some gradients that are of higher quality, then you can get there by taking larger steps and still get to the minimum. Where in this case, where we have smaller gradients which have more noise in them, then we'll be walking around a lot more. It will take many more steps since there are more noise to actually get to the minimum. So talking about noise comes from the signal to noise metaphor. This is actually something that is used in audio processing. The idea is if we have some very small batches, we'll have a lot of noise and not enough signal. Whereas if we have the batches too large, we'll have a great signal, but that just basically means the gradients will all be very correlated, and that's basically a waste of compute. So we want to be in a place where we have good signal to noise ratio. And this is rather crucial. Here we have a gradient A from here to here, and there is a variance on this gradient. And this is shown as an ellipsis here, where this variance, what we want to say is that the steps are correctly sized if the variance of the gradient is roughly on the same scale as the gradient. Meaning that if this ellipsis, if we take more batches, we'll get a tiny variance in here, but that's basically overkill. And if we take too small batches, we'll have some kind of huge variance, and then probably will go in the wrong direction. This is something, of course, all the things that I'm saying here are actually formalized mathematically in the paper. And so this variance here, the way this is calculated, is the trace of the Hessian of the sum of the losses divided by the gradients transpose multiplied by the Hessian multiplied by the gradients. I won't go into details what this means. I've basically forgotten what the Hessian is, but this is something you can totally calculate. And so here is another nice graph that tries to explain this. Down here we have the relationship between the batch size and the noise scale, which is basically where these two are on the same scale, which is what they predict is the optimal batch size. And for instance, if we go down to a batch size 1/100th of the size that of this noise scale, we'll see that as we make the batches larger, we'll just get a perfect scaling, perfectly better loss. But once we get above the noise scale, we'll basically have very little improvement in the gradients, but we will be spending way more compute. So the basic idea is the batch size should be equal to the noise scale, which is, well, precisely this, something we can calculate. There are a number of expected patterns in this. We expect that the noise scale will be larger for difficult tasks because the data points in more difficult tasks are not correlated in any simple way. So this is rather important. It means that the more difficult the task is, the more advantage you'll get from parallelizing this by having many batches. We expect it will grow during training. It will have a weak dependence on the model size. In theory, the formula that we saw before didn't include the model size as such, but we expect that a larger model will be able to obtain a better loss eventually, and that means that the larger models will be able to benefit from parallelizing more. So you can see both the factor up here and up here seem to somewhat counterintuitively suggest that the harder the problem is, the better it parallelizes. The more batches you can have. And there's something about the temperature dependence and how it varies. I don't think those are not quite as important. And then they have some experimental results which show basically that for batch sizes between 20 and 10 million, what we have here, this line here, they don't write what it is, but that's the x equal y, where they have the critical batch size where scaling stops working, and the the noise scale, the thing they just calculated, and it seems like the points are roughly along this line. So I would have liked some more work done here. I would have liked both to see the best fit among these lines, to see whether it is actually the noise scale or if it is something else. And in particular for some of the smaller ones, we should be able to basically do the Pareto curves for each of these. So instead of having these 15 points, we should have 15 Pareto curves. I think that would substantially clarify the problem. But I think the main point that they've shown here is one that is really, really interesting, that AI training scales better as the problem gets harder. And that's an unintuitive result that they soon, with both GPT-2 and GPT-3, would show that this, in fact, have very, very dramatic implications. That is all for today. Thank you and see you next week.